Okay, voltaic cells. Voltaic cells generate electricity. I kind of feel like we missed a slide. Did I miss a slide, Amanda? Earlier? Um, so we talked about electrical current. Current is the flow of charge, electric charge, and it's the electrons that are moving. So electrons moving through a wire, or we can have ions moving through a solution. The ions are carrying electrons. So redox reactions can be used to generate electrical current. So if we look at zinc and copper, zinc has a greater tendency to lose electrons than copper does. And so the zinc atom will transfer 2 electrons to a copper ion, and the result will be zinc ions and solid copper. It doesn't work spontaneously the other way around. Zinc just likes to get rid of its electrons more than copper does. And there's no simple way to predict that. We'll see, we'll have a table of reduction potentials that we'll just always look at, because you can't just know all this stuff. So the zinc becomes a dissolved zinc ion, the copper gets deposited onto the zinc. And so here's a picture of that. You put a piece of zinc into a copper sulfate solution, and this will happen. Now this doesn't look like shiny copper like is in your pennies, because it's not depositing in a nice organized fashion, but this is copper. And this is what we did, if you remember, in the experiment where we took copper through a whole bunch of different cycles, and at the end we had this real pretty solution, and we threw zinc powder into it, and it fizzed, and then it looked a little more like copper, but we got this, rusty brown stuff at the bottom, and the solution went clear because it took all the copper ions out. So the zinc atoms here are giving electrons to the copper ions in solution. They have to, get over here to get the electrons. And then the zinc becomes an ion and floats away, and the copper is not soluble, so it sticks to the electrode. Any questions? Oh, here it is. So we can separate the zinc atoms and the copper ions. There was no wires there, right? The transfer of electrons was happening directly between the atoms and ions. If we separate them and connect these two things with wires, we can get the electrons to move through the wire, generating an electric current, and then we can get that to do work for us. So that is called an electrochemical cell. It's a device in which a chemical reaction either produces electric current, or we can use electrical current to force a non-spontaneous reaction to happen. So a voltaic, or sometimes known as a galvanic cell, is where electrical current is produced from spontaneous reaction. An electrolytic cell is where electrical current is consumed in order to drive a non-spontaneous chemical reaction. So this is an example of a voltaic cell. This is going to generate electricity using the copper and zinc reactions. So here we have, and this is just a real simple setup, we got 2 beakers here. This side has a solution of zinc nitrate. Nitrate does not do anything here. It's just the counter ion for the zinc ions. And over here, we've got copper nitrate. Again, just a counter ion. Why do you think we use nitrate? Think about the solubility rules. All nitrate compounds are soluble. So we'll see that as a counter ion a lot. So we have a piece of zinc metal stuck in here and a piece of copper metal stuck in here. And we're connecting them with a wire that goes through a light bulb. And so when current flows, the light bulb lights up. Neat, huh? So the zinc is being oxidized. It's losing electrons. What's really going on here, we can think about this in terms of equilibrium. Yeah, none of those things actually go away. We keep talking about them. So here, if we look at zinc in equilibrium with zinc ion, copper in equilibrium with copper ion. The equilibrium for zinc lies farther to the right. It has a larger equilibrium constant. And for copper, it lies to the left. It has a small equilibrium constant. So what happens is, even when these aren't connected, there will be a little bit of negative charge that builds up here because the zinc atoms are releasing electrons. They just don't have anywhere to go, so they kind of build up, and then with Chatelier's principle, you get too many electrons and it's just going to stop there, right? And over here, this is going to build up a slight positive charge. So when we connect these, the electrons want to go away from the negative charge and travel to the positive charge. Does that make sense? And that will happen until each half cell reaches equilibrium. We'll talk about this guy in a minute. So the half cell is connected by the wire, electrons spontaneously flow. The zinc ion equilibrium will shift to the right because the electrons are being removed, and it'll keep going. And the copper will switch to the left, shift more to the left. And so it will keep going until we run out of an ion. So electric current, we can use water as an analogy to help us understand electric current. So if you think about, the Kings River, right? Why does water move from like Pine Flat Dam down the river? Gravity, right? The top of the dam is higher than the bottom of the dam, right? And so the water wants to go to a lower potential energy. And the slope of the river itself is generally going down, and that's why the water flows. Same thing in the canals. So if you're into stuff on the river, you sometimes will look at the water flow because you want to know what's going on with the river. And you can check it at several different places and tell you how fast the water's moving. So we're also interested in the rate of electrons moving, which is just like the flow rate of the river. And we measure electric current with a unit called an ampere. And you're probably familiar with the abbreviation amps, right? And this is not the amplifier for your electric guitar. This is amp, short for ampere. That's a unit of electrical current. So it's how fast electrons are moving, but instead of counting electrons, we use a unit called a coulomb. And we kind of mentioned that back in Chem 1A, but the coulomb is a unit of electrical charge. So an amp is the rate of electrical flow. So 1 amp is 1 coulomb per second. And a coulomb is 6.242 times 10 to the 18th electrons. So an amp is that many electrons moving per second. So we know that water current is driven by a difference in gravitational potential energy. Electric current is driven by a difference in electrical potential. Okay. So a measure of the difference in potential energy per unit of charge. So that's, the ampere is charge over time. The difference in potential energy is its energy per unit of charge. And so that unit is the volt. It's the unit of potential difference, and it's equal to 1 joule per coulomb. This is the beauty of the metric system, where all the units just, fit together nicely. We don't have weird numbers like 12. So if we have a large potential difference, we'll get a strong tendency for electron to flow. Big potential difference between the two electrons, strong tendency for electrons to flow, just like in a steeply descending stream bed. The electromotive force, which is abbreviated EMF, is another term used to describe the potential difference. This potential difference is a force that results in the motion of electrons, so electromotive force. So we can talk about the cell potential, so the potential energy, or cell EMF, is going to be the difference between the potentials of the two electrodes in the two different cells. Two different half cells. So the cell potential is going to depend on relative tendencies of reactants to undergo either oxidation or reduction. In the previous example, we saw that zinc was oxidized more easily than copper. It was more willing to give up its electrons. So we get a high positive cell potential when we have a substance with a high tendency towards oxidation paired up with a substance with a high tendency towards reduction. Like, this guy is really good at giving up electrons, this one's really good at getting electrons. We'll put these two guys together and be really happy and get a lot of transfer of electrons, right? It also depends on the concentration of the ions and the temperature, right? And that kind of goes back to some previous chapters we've talked about. So as with enthalpy and free energy and entropy, we need a standard definition. So the standard cell potential, and here's that degree symbol again, that means the standard cell potential, is going to happen when our cells have concentrations of 1 moles per liter or pressures of 1 atmosphere for gases. Okay, so which statement best captures the difference between volt and amps? The volt quantifies difference in potential energy. The amp is a unit that quantifies flow. Choice B is the opposite of that, and choice C is saying they're the same thing. They both measure flow of electrical current. A. So volt is a difference in electrical potential energy. Amp quantifies the flow. And amps are something that you're interested in when you're getting a charger for your cell phone, right? You can get a 1 amp charger or a 2 amp charger. A 2 amp charger, the electrons can flow twice as fast. Your device is going to charge faster. That's the answer. So in the previously discussed voltaic cell, where we had zinc and copper, if we have the zinc is more easily gives up its electrons, and copper is more willing to take them. And so that the standard cell potential there, when these concentrations are 1 mole per liter, will be positive 1.10 volts. If we change out the zinc and put nickel in, we're still going to get spontaneous reaction, but the cell potential now is 0.62 volts. Because nickel is not as willing to give up its electrons as zinc was. If we get a negative cell potential, that means that the forward direction is not spontaneous. It's actually going the other way, right? It's going in reverse. Any questions? So here are some terms, and you might want to take a screenshot on, not of that, but pull up the slides from Canvas and take a nice screenshot so you have this as a picture. So we have oxidation, reduction, we have anode and cathode, and we have to remember which way things are moving and what charges things are. So oxidation occurs at the anode. The way I remember that is both of those words start with vowels. Okay, oxidation and anode. Reduction occurs at the cathode. Those are both consonants, or think about a red cat, right? Red cat. The anion is going to be more negatively charged. I remember that by thinking about, well, anions are negative. Anions, anode, the anode is the negative one. The positive one is the cathode. Cations are positive, right? Positive. So the electrons are going to flow, yeah, right. I wasn't getting a laugh, so I had to kind of emphasize that one. Electrons are going to flow from the anode to the cathode because the anode is negatively charged and the electrons are negatively charged, and we're like, we want to get out of here, right? And there's a positive charge over there, and ooh, we're attracted to the positive charge, okay? So we need to be able to deal with these words. I don't expect you to instantly remember which one is positive or negative, because I have a hard time with that. And I teach the class, right? It's confusing. But if you have a way that you can think it through in your head, then you can come up with the right answer in like 5 seconds or something, and that's pretty good, instead of just wild guessing. So if we had electrons flowing from the anode to the cathode, eventually we'd build up a charge, right? Because we've got electrons moving in one direction, and everything's going to stop. So this is what I said we'd talk about later, a salt bridge. So a salt bridge allows counter ions to flow between the half cells without the cells actually mixing. Because if it was all in one beaker, the electron transfer would be direct, and we couldn't get the electrons to go through the wire, and then they couldn't do any work for us. So this way we allow the ions to move through this salt bridge without things mixing. So we've got electrons going from the anode to the positive cathode, and then the copper ions, right, are getting the electrons and forming copper metal. And so we need something to carry negative charge back to the other side, and so that will be the anions, the nitrate ions. Well, why would they move? Well, because this thing is positive and they're negative. Like, get away. And the only place they can go is through the salt bridge. So this is the same picture we looked at earlier, but now we're going to talk about this. So here we have this salt bridge. And so we've got electrons going this way, and the negative ions are going to go in the same direction, right? And some positive ions will flow in the opposite direction. Because a positive moving in the opposite of the direction of a negative is really kind of the same thing, isn't it? So this can be made really simply by using sort of a gelatinous substance here that has salt in it, and you can put a glass wool plug at the end to keep it from just kind of all running out. But the ions can pass through, and so the nitrate ions are going to go this way, and potassium ions are going to go that way. Any questions? Obviously, that's not what's inside of your battery. So in a voltaic cell, which direction do the electrons flow? From higher potential energy to lower? From the cathode to the anode, or from lower potential energy to higher? It's A. Does a weight move from a high position to a low position, or from a low position to a high position? In my keys. If I let go, what's going to happen? Are they going to fly to the ceiling? No. They go down, right? because the floor has lower potential energy. So the electrons are going to go lower potential energy too. Choice B isn't right because the cathode is positively charged and the anode is negatively charged, and they're attracted to the cathode. They're going to the cathode. Huh. So we can also think of it this way in terms of water. Here we have, two beakers connected with a tube. And so this has a high potential energy and this has a low potential energy. And I think we all know intuitively, just from our life experience, that the water's going to flow in this direction until what happens? Until they become even, right? Well, it is 6:15. Oh. We'll just save those for next time. We were actually only supposed to get through section 20.2, but we were just rolling along so nicely. I thought, well, let's just see where we can go.